Hello students, in this lecture we will discuss about some, uh, some of the optical properties. We'll first start with the term called plasmonics. Plasmonics is dealing with metallic nanostructure and application. Now, in metal nanostructure, the optical properties are compared to bulk form and not derived from quantum confinement of holes and electrons, rather from electrodynamic effects. So, if we consider metal nanoparticles or nanostructures, electrodynamic effect is predominant on confinement, and modifications of the dielectric environment. So one is electrodynamic and then is dielectric environment modifications. They are more effective in metal nanoparticles compared to confinement of electrons and holes. Now we are dealing with plasmonics since a major manifestation of oscillations of electrons are localized along the surface. So we are mainly concerned with electron oscillations. And these oscillations for metal nanoparticles are localized along the surface. Hence the term surface plasmonics. And there are also waves associated with surface plasmonics, and they are called surface plasmonic waves. Now, the metallic nanoparticles that we talked about, these metallic nanoparticles, they can be nano rods, they can be nano shells, they can be nanoscale films, and they can be even islands. So when light falls on a metal nanoparticle, there are oscillations of electron already present. So light basically is an electromagnetic wave. So interaction of this electromagnetic wave takes place with the pre-existing electron oscillations. So these two interact with each other and interfere. So that is why the oscillations are also called the plasmonic wave. And in metal dielectric interface, metal dielectric interface. Then surface plasmons are more dominant, or surface plasmons are more active. Now there are some characteristics of the surface plasmons. Why is it totally different from normal plasmons? So these these plasmons are only excited by the special geometry required for matching with the surface plasmon wave vector. That is, require a special geometry. And there is a surface plasmon wave vector which is called KSP, and while this is the surface plasmon wave, in metal nanoparticles, the plasmons are localized and not categorized by KSP. This is only for the surface plasmon. Unlike the surface plasmons, the specific wavelength of light absorption producing plasmon oscillations are called surface plasmon bands. So there are some specific wavelengths. Which produce plasmon oscillations. And they are called surface plasmon bands. Metal nanoparticles have got photonic applications. They have got local field enhancement. Then there is what is a local field enhancement? The light can be coupled with propagated through electromagnetic wave through a dimension much smaller than the optical waveguiding dimension, and so due to this smaller optical dimension, there is light local field gets enhanced. So there is a light absorption also in nano wavelength range. and there is resonance with surface plasmons. And depending upon the shape of the nanoparticle and the dielectric environment. So here again, what type of resonance, whether resonance will occur or not, again will depends upon the two factors. First of all, is the shape of the nanoparticle and the dielectric environment. Now let's take some example. Now say there are very small nanoparticles of gold, say of 25, less than 25 nanometers. Now today there is a shift of surface plasmon band, peaks is small. The shift of peak, surface plasmon peak. However, a small shift, the shift is very small. However, so first of all, there is a broadening of the band is also observed. So first characteristic is a very small shift, and the second characteristic is broadening. So a larger, if you increase the size of the nanoparticle, for example, if the nanoparticle size is greater than 25 nanometer, then we actually get a redshift. Redshift indicates moving towards higher wavelengths and lower frequencies. So, if you plot the absorbance versus the wavelength, get a plot like this for say 9 nanometer gold particles, and on increasing the size, there's a small shift. The small shift towards the higher wavelength, and also there is broadening. Okay, so this is what is observed. Now, as we said, that there are two factors on which the resonance will depend. The shape of the nanoparticle is also very important. The shape is important because, for example, if you have a nanorod, which has two dimensions. First is the longitudinal dimension, and another one is the transverse dimension. Now, the plasmon band actually splits into two oscillations, longitudinal and transverse. So, according to that, there will be longitudinal and transverse oscillations as well. Some oscillations will be longitudinal, some will be transverse. So, longitudinal and transverse oscillation. These are the two oscillations that will take place. And due to this oscillation, the observance will show two different peaks. So if you plot the observance, versus lambda 2 peaks will be observed. This one is for the transverse and this one is for the lambda. Now, as you have said, the shift is actually not due to quantum confinement. The shift of the band is not due to confinement. It is more of electromagnetic in nature. Now, when in electromagnetic field, electrons are under oscillations. When they are on oscillating dipole, and in wave, the electrons are oscillating, and these oscillations of electron, they create something called an oscillating dipole. Dipole is positive and negative charge is separated by distance. This is a dipole, so this oscillating dipole means the polarity of the two ends is keep on changing. And due to this effect, the electrons are driven to the surface of the nanoparticle. So it can be visualized like this. So if this is a metal sphere, and and there is an electron cloud surrounding it. So the electron cloud actually shifts upwards as we are providing an electric field. Sorry, this is the metal sphere. So on application of an electric field, say in this direction, the electron cloud in this case shifts downwards, and this case shifts upwards. So this is how the change electron cloud take place with electromagnetic radiation. And so this type of displacement gives rise to something called an extension coefficient. And it is given as KEX, and the rule of this extension coefficient is that it it's a measure of absorption and scattering strengths collectively. It's a measure of absorption and scattering strengths collectively. And it is mathematically expressed in the following manner. So K extension is equal to 18 pi n V epsilon H to the power 3 by 2 divided by lambda multiplied by epsilon 2 epsilon 2 plus 2 epsilon H plus epsilon 2 whole square. Here epsilon H is a dietary constant of the surrounding medium. Between epsilon 1 and epsilon 2 are really the imaginary parts of the dietary constant. So this is the real part and this is the imaginary part. So epsilon m is equal to epsilon 1 plus I epsilon 2. And this total dietary constant, it depends on the frequency of light. So this is the total dietary constant. Now, surface plasmon resonance absorption is produced at optical frequency when the resonance condition is satisfied. So when epsilon 1 is equal to minus 2 epsilon H, now the size dependence of the surface plasmon resonance. So this is where the surface plasmon resonance is produced. Absorption is produced at optical frequency omega. So it implies surface plasmon resonance absorption is produced if this condition is satisfied. Now the size dependence of the surface plasmon resonance comes from size dependence of dielectric constant of the material. Now since the dielectric constant is size dependent, is size dependent, so that is why the SPR or the surface plasmon resonance is also size dependent, and This dependence of size is also known as intrinsic size effect. Now, this was all about the metallic nano rods. When we have discussed about metallic nano rods, there is longitudinal or transverse modes. There are geometries which affect the frequency of light. For example, if we are dealing with something called a metallic nano shell. Now, it's called a nano shell because there is a dielectric core which is surrounded by a metallic shell. So this is the core, and this one is the metallic shell. So this is what is a metallic nano shell. Now, in this condition, if you take the absorption spectra, then it will show a red shift. It will move towards higher wavelengths. And as the metal thickness decreases, we also get redshifts. So we can get redshifts in two possible cases: when we are forming a nano shell, size of the metal nano shell is decreasing, and if we are depositing a film and the metal thickness decreases. For example, if there is a dielectric core, as there is a metal shell, if the thickness is metallic shell, if the thickness also decreases, then also we will get a reaction. Go to the shift. So these properties of nanoshells are used in linear and nonlinear optical spectroscopy. Its applications are linear and nonlinear optical spectroscopy, and then it has applications in field enhancement for nano spherical particles. Then metallic films can cause transmission to coupling of light, and there is also plasmon guiding. So, there is a application occurs in photo oxidation. Then there is field enhancement, as already told. Then metallic films and holes of high optical transmission due to coupling of light to surface plasmons of both sides of the metallic film. So there is a coupling, as already told, and thus there is something called the plasmon guiding. Plasma oscillations in one metallic nanoparticles induces plasma oscillations to the neighboring nanoparticles. So if there is a one metallic nanoparticle, so there's some sort of plasma oscillations going on. So it will induce some sort of plasma oscillations are going on. So it will induce this effect onto the next metallic nanoparticle. So this is known as a plasmon guiding. So these are the different effects of plasmonics, that is plasmonics in metal nanoparticles.